And I came up with stacking of spheres, different arrangements in a hexagonal arrangement, or what I call now the cannonball stack, which is a different stacking of spheres. But if I know the height of the stack of spheres, of 14 spheres, I can figure out what the radius of a sphere is and then the base area of it. And those are the two parameters that are needed for the Huray model.
Hello, everybody, and welcome to the Altium On Track podcast. I am your host, Zach Peterson, and I am here today with Bert Simonovich of LandSim Enterprises. Bert Simonovich is a well-known signal integrity expert and someone who I have cited in quite a few conferences and papers, and I'm very excited to talk to him because it's not very often that you get to talk to somebody who you have cited. Bert, thank you so much for joining me today on the On Track podcast.
Well, thank you for having me, Zach. Nice to see you.
Nice to see you too. We've chatted over LinkedIn a little bit, and guys like you always keep me on my toes, so I appreciate that.
No problem.
So, you are well known in the signal integrity community as someone who has very eloquently explained stubs and someone who's very eloquently dealt with roughness on interconnects and then also on the plane, which I think people don't often think about. But maybe before we talk about some of your work in those areas and any other areas, maybe you can introduce yourself for the viewers.
Okay, thanks, Zach. Yes. I'm a graduate from Mohawk College in Hamilton, and I've been involved with a lot of different things. I joined a startup after I graduated. We did microprocessor systems back in the late 70s, and that lasted not too long. I got a job up in Ottawa, Canada, for Bell Northern Research, and I stayed there pretty much my whole career. It transitioned over to Nortel in the late 90s and held a variety of engineering and different positions there. At the end, I specialized in backplane design and signal integrity. I started more so specializing in that. And since then, I've been focusing mainly on signal integrity and started my own business in 2009. LandSim Enterprises, where I do consulting now for clients.
So do you consult in board design? Is it signal integrity? Is it a little bit of both? I mean, are you in the layout tool, laying stuff out every day?
Oh, no, I'm not a PCB designer per se. As I said, I graduated electronic technologist. Actually, when I first joined Bell Northern Research, I worked on T1 line repeaters. And my task, we had a small team, 3 of us. I started doing the actual layouts in PCB layout. I learned how to do that. And back then there wasn't CAD like we know today. It was, you laid it out with Mylar paper. First did it with pencil, colored pencils, red and blue. And then you taped up the Mylar after and took photo reduction. It's just 2-layer boards. And made the photo tools, what we call photo tools. They're the positives and negatives to make the boards.
So it's the analog version of photo plotting that we do with Gerbers.
Yeah, exactly. Back then, there were actual photo tool, hard negatives and positives, camera done. We did things in 2-to-1 scale and photo reduced to the actual scale itself. So that was actually a real good education, really, because I learned about PCB layout and design, and that has helped me entirely through my career, actually, to understand, the mechanics of PCB construction. So I still apply those same principles today when I do like backplane design. It's more at the architectural level, the high end, where I plan out all of the routing, number of layers, how to route the tracks, but I understand the aspects of the PCBs, and we have excellent CAD people. That was their job, 8 hours a day to do layouts, so they're expert at doing it. So if you give them what you wanted done, they would just implement it and get done. So it was helpful in that respect. But what I do now, it's a variety of things. Some clients call me up, ask me to help them with their design reviews before they tape out the board. They want sort of a last look. Or they've had some issues with some boards. They've recycled several times. And sort of have a look at it and see if you can, identify any issues. And I found some issues with some clients that way. It was pretty good. Not too much backplane, as I say, although back in 2013-ish time frame, I worked with Via Systems, and which is now, they've been bought out, PCB shop. And then right now, the company that developed the XMX connector, it's now Amphenol. We did a exploratory kind of backplane as a demo backplane because they were going to introduce the XMX connector. And that was a successful collaboration, actually. We developed this small backplane with a couple of daughter cards. And the nice size of it was portable, and and it ended up being every DesignCon since then. That platform was there. Mainly Surdes companies wanted to demonstrate their Surdes, because this was meant initially to be 25 gig compliant at that time, NRZ. That's when the standards were coming out, and so it was meant to have like a stressed length, like 36 dB and then plus to do things. So so it's very successful that way. And so that was that part. So mainly now it's focusing on signal integrity. I'm engaged with a sort of a long-term kind of client where I help consulting with them for high-speed signal integrity on serial link stuff now. That's really what I focus on. And so that's sort of part-time of the week. And the other parts of the week, I continue my research.
And so your research focuses on which areas?
Okay, so my pet program, as you've identified, is actually roughness of the copper and its effect on the signal integrity. And I started on that actually as a result of one of my early clients who wanted me to do a study on dielectric material comparisons. But they wanted to include foil roughness. And at that time I thought, well, I'm just doing A to B comparison. What does roughness have to do with it? But they wanted it anyway. And I didn't really understand the effects of any of it. So I started doing some research on it and applied, what we had at the time, really the hammer stud kind of equations to things. And it worked out all right, but it kind of sparked an interest because once I got started with it, and the more you dug into it, the more you wanted to try and model it correctly. And I got into the Huray model. But the Huray model was difficult to use, although it was very accurate. So I started to research to find a way to come up with the parameters from data sheets without kind of measuring. Because when it was first introduced, the idea was you would sort of take SCM photos of the surface topography and try to estimate the roughness from there and kind of put in the parameters. And if you had measured data, you would kind of tune the parameters to the measurements to get to get them to work out. But if you didn't have the measurements, the Huray model is pretty much useless because people wouldn't know what to do. So anyway, I started trying exploring ways to perhaps do it. And I came up with stacking of spheres, different arrangements in a hexagonal arrangement, or what I call now the cannonball stack, which is a different stacking of spheres. But if I know the height of the stack of spheres, of 14 spheres, I can figure out what the radius of a sphere is and then the base area of it. And those are the two parameters that are needed for the Huray model. And I tested it out. I got some data from friends of mine, and I kind of worked on it from there. And when I tried it out, it worked out really well. But again, that was just one set of data. At least I presented it at DesignCon 2015 at the time. And it kind of has been percolating ever since. So ever since, whenever I got more data, I was able to test it out and find out how well it was. It worked out very well.
So when you have so many models like this, I mean, it sounds like you may have figured out the answer, but when you have so many models for roughness, how do you choose what is objectively the right one to use on the front end before you've ever built a prototype or before you've ever done any sort of channel measurements? Do you have to rely on maybe, I don't know, a manufacturer to determine that, or do you have to just get material samples and, do some kind of testing yourself? I'm wondering what's the best way, or are you forced to spin a prototype with maybe a test channel and do the measurements, correlate to the best model, and then say, okay, that's the model that's going to work with this board, with this process going forward?
There's two trains of thought. Some people advocate that's the only way that you would get it. It is a way, but I call that method design feedback method, where you design a test coupon and you build the coupon, do the measurements, V&A measurements, make sure you have good S parameters. Then you cross-section it after, take accurate measurements of the thicknesses and the roughness and everything, and you tune your model to it. If you didn't have my Cannonball model, you would tune it to it. So you'd end up with DK, DF, and roughness to put in. And you'd go from there and you say, all right, next time I make this stack up with this exact material and line width and space, I'll use these numbers. The trouble is with that process is you get one board shop, they would build it, and they have different oxide or oxide alternative treatments they put on. And you don't actually know how well that is. So sometimes, depending on the process control, it can be good or can not be. Or if you have another fab shop, they use a different oxide alternative. One may be just an etching type where it actually etches the copper. And that's the worst because it changes the actual copper profile, as opposed to just an oxide, which is non-conductive. It adds roughness, but the underlying profile doesn't change. So, if you did your characterizing with one board shop, and then, how large companies go, they have purchasing departments and want to go to cheaper board shops, they'll send it out somewhere else and get fabbed, and you get it back, and surprise, you may have some issues. It's not what you expected. And actually, I've come across that with some of the work I've been doing with the clients. Every time we kind of build a new design, I put in test structures to kind of validate my model, which is good. And I found even with the same manufacturer, it was a different design, but the same manufacturer a year later, when I went under the microscope, the roughness of the foil was different. But it's the same laminate, same foil that's supposed to come. So you have tolerances on the foil itself, plus you have tolerances on the oxide treatments. So that's that process. I mean, it's, and it takes a lot of time and money to do it. So why I developed my process is because I'm in consulting. I don't have access to do all of that. I don't have a VNA, 50 or 60 gigahertz VNA to do the measurements and take the time. I don't do the layout or everything. So I help clients even at the front end of the design. I work with the architects when they come up with a new box, they have a new SerDes or new switch chip or something. And they're coming up with, how it has to go. And a lot of it is top of rack pizza boxes, which are, 19-inch rack mount. So you have a loss requirement from the chip to these modules, which you have to meet. So you have to work with them and kind of build up a topology channel model of that structure and see if that architecture is going to work. So, this cannonball technique, I've dubbed my modeling method now as it's a heuristic method. And heuristics mean it's not guaranteed to be perfect, but good enough to get there. And it's based on data sheet parameters. It's not just out of the air. It's a structured approach. You get the data, you put it together, and you do the modeling. And then after you kind of build it, you can build a test board, to kind of validate it. But, at this point, I'm pretty confident it has been working out. And we put the test structure in on the other board, first prototypes, to kind of validate it. And for the most part, it works out. Most of the time, I'm more pessimistic than I get it, then the board comes in. And when I go under the microscope and I actually do the cross-section measurements and then put those numbers in, it then lines up perfect, pretty good. So that's, the loss aspect and why we do it in that respect. But then, over the years, I've also realized the roughness affects the effective decay of the material. So we all know decay is important for impedance control, all of that stuff. So the rougher the copper and thin dielectrics now is why you get difference of your phase delay or even the effective decay that you would use in your model is because the thin dielectrics we need these days. So, that's part of the research I've been doing on it. And it's always iterative. And always finding I'm learning a little bit new things as I go. Quite recently, last year, was actually, I was talking with my friend Al Neves from Wilder Everett Technology. He does test platforms. That's his business, Signal Integrity. We were talking about it and, I explaining it to him and, we had some discussions. So I said, well, send me some data. I want to test my model out on some of your platforms, your platform you're working on. So he did. And when he sent me the thing, I noticed the stack up that he was using. One of the reference planes was a rougher copper than the signal layers. And to me, when I always modeled, I always made sure everything was the same roughness. So I never really thought about it too much until I saw this and I go, oh, that's different. So it was an excellent platform to test out the model with it. So, the difference of the roughness of the planes factors in now, and you can see the difference in it. So it worked out really well.
Yeah, and you have some Signal Integrity Journal articles focusing on some of these points. So I invite anyone who is watching or listening to check out the show notes because we will link to those articles because I think they are a great read, and you definitely do a great job of explaining a lot of this stuff. One question that just came up because you mentioned the oxide. I'll admit I normally, when I look at this type of thing and doing any kind of, or building any kind of model around roughness, the oxide is not normally considered because you have mentioned it is non-conductive, and I think there is a natural assumption that the roughness is on the trace, meaning on the conductive copper. And so when you apply a correction factor, you would then, does that assume that all of that roughness is all on the copper, or does it
So
account for the oxide only, or is it a combination?
the way copper is used in many of the most of the PCBs today are electrodeposited copper. And electrodeposited copper has two sides of the foil. They have the matte side, which is the side that comes out of the solution, and that's a rougher side. Then they have the drum side, which is the smoother, some people call it shiny side or whatever. That's the side that gets the treatment from the board shop. And the matte side gets treated with usually tiny nodules, and that's the side that gets bonded to the core laminate. So the core laminates that you buy, double-sided copper core, has the treated matte side bonded to the dielectric. So that's fine. That goes to the board shop. They etch your patterns onto each side of that foil. Now they build the stack up and they glue everything together with the pre-preg. But before they use the pre-preg, or before they glue it together, they apply some roughening treatment to the shiny side. So traditionally, there wasn't oxide treatment. It was just oxide was non-conductive. But many suppliers, certainly in the US, had gone away from it. And then they have this oxide alternative. And oxide alternative actually etches the foil and makes it rougher for adhesion. And there's different chemistries that's used for it. And that's the point, is when you roughen the actual foil, now the foil has this actual roughness to it, and it affects the propagation delay. Actually, the roughness adds extra inductance as well to it, and makes the delay a bit more. But that's what affects the loss, is that actual roughness of the foil itself. So that's what you don't know, what board shops, what they use. And even worse is, what number do you use for that? That's the hardest part. You can usually get from the laminate supplier what the treated side of the foil, like an HVLP type foil, would have like a 1.5 micron roughness on it. And I, use that RZ number, not RMS, it's RZ. That's what you find on data sheets. And you apply that to my Cannonball, and it works out. But the other side is hard. Each board shop has a different chemistry as well. So what I do is, in 2016, HD Pug, High Density Packaging User Group, is a kind of consortium of different companies, and they do research on PCB materials and different issues. But they did a study on oxide and oxide alternatives in 2016. They published a paper with that information. So typically, if I don't know, I will use sort of what the worst case number I got from that study. And it's usually not too bad. But if you do know, or if you kind of do research and read other papers, other people have done other studies, actual measurements themselves, and you kind of get a feel for all of that stuff. So you kind of work in that range. But the higher speeds now, when we're going, say, to the 112 gig, perhaps, we may have to go to the non-etch type kind of bonding. It's a chemical bonding where it doesn't actually roughen up the copper, but it's actually a covalent bonding to the material now. So that's maybe what we'll have to go to do. So.
That's interesting, and the reason I asked about the oxide is because if it is an oxide treatment, right? The oxide is non-conductive, but does create roughness into the dielectric, and so the result is that you've basically got field confinement into a slightly smaller region in the dielectric.
No,
I mean,
actually,
it
it's the
changes the
actual
dielectric constant.
copper roughness. If you think of the teeth, they are conductive, and to get your fields, you need the electric fields. So if you have these points going in there, it's the actual points that are making the effective thickness less, right? Yeah, yeah. So it's the conductive one. When you
Right, that's
etch
what I
the
mean.
copper,
That's what I mean.
it does that.
Yeah.
That's what causes the extra higher decay. But the oxide that's non-conductive,
Sure.
if the underlying profile is still smooth, it's still okay. It doesn't change as much from your data sheet, is what I'm getting at. And that's why the actual roughness of the
Yeah, I
copper
see.
is important. Yeah, yeah,
That's what I was getting at. Yeah, is if there's a difference
yes,
between the copper roughness versus like the
yeah,
oxide surface on
yeah.
top of it, does that make a difference? Okay, so I'm hearing it doesn't. Well, and it sounds like that, that copper oxide layer is going to be so thin compared to the dielectric
You say,
anyways.
yeah, well, yeah. So that's
It wouldn't
oxide is
really
just
matter.
like rust, really. It's different property than the dielectric, but well, I haven't done any real studies, to know how much difference it is, but I suspect it's quite small as far as, because it's really thin, non-conductive, very thin. It's different than the dielectric, but
Exactly.
it's certainly, I don't think it is huge. Yeah, yeah. And this
Yeah,
is only true for like thinner
negligible effect.
dielectrics. The thicker the
So
dielectrics, the
you
less effect the copper teeth or the roughness has on it. So, right.
yeah, and you had a nice simple approximation for the effect on the dielectric constant, which I've always thought was very useful. And you're right, it is a smaller effect when you have the thickness of the dielectric and the
Yeah.
roughness more dissimilar. So one thing that you had kind of alluded to here was like a worst case number or a worst case analysis. And so I'm wondering here if you're going to if you're going to develop a design process around this where you're working with your fab and you know that okay the tolerances on the copper roughness and the processing parameters are going to change somewhat over time as you mentioned, and they'll also change from vendor to vendor. If you can put some limit on an acceptable roughness that you would accept from a fabrication house, let's say, can you use that and say, okay, we'll accept this maximum amount of roughness, and anything under that we're okay with, and then model to that and use that worst case for channel modeling? Is that do you think that's a good approach to try and, at least get some sort of I don't want to say consistency, but get some sort of standard by which you can design to?
That's sort of what I do when I do the channel modeling. That's why I use the HD pug numbers, because they seem to be maybe higher than normal. You don't necessarily get a range of things, so I typically would use those numbers, and I build the channel model up. And if I met the loss budget, at least initially, I say we're okay. And of course, we build the prototype and validate it as well, to make sure. And most of the time, it's a little better than I had predicted, which gives us even more margin. So I like to kind of I like to try to get a worst case rather than a best case, because the best case, if you do things, you could end up in trouble. So, but it's hard to get. And if you stick with the same board supplier and work with them in the same material, over time, if you built structures, you'd build your own kind of database yourself and kind of know all right, this time, you have some sort of statistics of that number and you could work with, right? Uh, Certainly it's there. I mean, the foil itself, when you try to ask the laminate supplier of the foil, they only give you sort of one number. But if you kind of go to the board shop, and they can get other numbers from the foil supplier that have some statistics associated with it. And for one foil, that I looked at, published on their data sheet is sort of like 1.3 or 4. But statistically, I got some data, and it was anywhere from like 0.7, to 1.6 or so, the statistical distribution. And, sort of the mean was around 1.2 or 3. So it was sort of under what they had kind of put in their data sheet, what they do. So it's okay. So that tells me if I use the higher number, I would be all right with it. So I'm comfortable with, this process. As I say, it's heuristic initially because you get those numbers. You have to start with something. Just like when you do your stack up, use the DKDF tables, use those numbers to do impedance prediction, and But actually, when you get the board and measure it, it could be different because there's variation in that dielectric as well, and the process, from the fab shop. So it's it all ties together. PCB construction is complicated.
Yes, it is. And I've been trying to make it my mission this year to learn more about the guts of the PCB fabrication process. It's something I think every designer, SI engineer, whoever you are, should definitely know about. But you brought up something interesting, the statistical distribution on, yes. I think it was RZ values that you were referring to. So that seems like a really broad distribution, right? I mean, you said like 0.7 to maybe 1.6. I'm assuming that's two standard deviations.
Yeah, it was there. As I say, the mean sort of landed at about 1.2 or 3, in about that range, which was under what they kind of published on the data sheet anyway.
Okay.
So, and actually, when I did measure the one board, the roughness on the treated side was actually under a micron on that sample. And that's why when I had measured the board, my prediction for that was worse. And then when I cross-sectioned it and actually used the numbers of the cross-section and put back in the model, then it brought it right back to what it should have been. So, yeah, it's...
Sure.
And if you kind of had measured this board first, let's say that was my prototype, right, for this design feedback method, I would have said, oh, the RZ roughness is 0.8, right? And if I use 0.8 in the future, I could get a board where it's 1.3 or 1.5. My loss would have been worse. And my impedance would have been different, So, yeah.
Yeah. It almost seems like it doesn't seem, it sounds like a very time intensive task, because after the board goes through processing and it's a specific stack up, right? You've just said, right? You could measure one board and get one value for roughness, but the true statistical distribution may say the mean is something higher or something like this, right? So you design to the low number and maybe you have too much loss, or your channel falls out of compliance. I don't know what the result might be, but regardless, you're designing to the wrong number. So, I mean, can a board shop maybe provide some more value specifically to high-speed designers by, I don't know, taking their standard stack-ups and, measuring 100 test coupons and getting maybe a more accurate number? Or is this just too much work for them and they just want to say, hey, SI guys, we don't want to deal with this, you handle it? The laminates or the foil supplier said this, so we're just going to go with that.
The board shop might have done studies on the roughness of their their oxide treatment. I'm just going to use oxide as a general term, treatment. They might have got it,
Sure.
or they've done it, or they don't necessarily want to share it with everybody. So it is kind of hard. It's really, you need to, what I ask them for is the actual cross-section pucks that they do. For the stack up, they send it to me. And I've got my own microscope. I got a good one last year just for this purpose, where I can do the measurements myself. And, so I get it, I do it myself that way. But it's hard. One thing I do know, as we go further and further into it, you need to work with your board shop from the beginning of your design. If you're planning a stack up, you can come up with your own preliminary stack up if you understand what it is. You have your own tools. I do my own preliminary one because I know how many layers I will need, how many power layers. So I'll do a preliminary one in the material I want. I'll work with the board shop and hand it to them, and they'll sanitize it for me and say, oh, no, we don't want to use this glass style because it's whatever, because of their process. They need more resin in it. So they'll come back with something slightly different. They've adjusted the thicknesses properly for their process, the press thickness. And then, I'll run those numbers, and we work back and forth, and we agree on the stack up with it. So, it's important to start early with your board shop and partner with them instead of going through the design and handing it over the fence. And then they'll come back and say, we can't build this. And then it's too late. So for signal integrity, if you're doing your modeling, you need to work closely with them. And when you do, then you can probably get the numbers you want from them, working this way.
Or at least you can prevent some double work, because you're going to know a nominal DK value or have the DK/DF tables ahead of time. You're going to know let's say the roughness that you can expect reasonably within some delta ahead of time. And then instead of waiting until the end, you hand it off to them and they say, hey, we can't build this stack up. This is what your DK is actually going to be. This is the foil we have to use. And then you have to go back and redo the modeling and make sure that whatever is going to work and whatever you're going to put into that modified stack up is still going to work.
Try to avoid double work. Exactly.
Yeah. Yeah, absolutely. I'm sure.
Yeah.
I know clients don't like to pay for
and also,
double work.
When you've done all the homework up front, your probability of first time success is greater. Obviously there's little things that crop up.
Sure.
But
Yeah,
there
of course.
should be really no big surprise when you get your first prototype. At least that's what I found. So.
Yeah. Okay. So you've mentioned in the we talked briefly about the roughness on the trace versus the plane, right? And how they can be different. Is the difference just due to the foil type in one laminate versus the other?
Sometimes
just
when you
that
build
simple?
a stack up, you have your core laminates where you have your, the traces on one side, and if it's a reference plane is on the other. So it'll be a ground and a signal layer on it. But when you laminate it to another core in between the prepreg, when you're near a power layer, say you're near the center of the stack up, that power layer might be thicker material. And generally people say, well, that's not high speed, it's just power. So they may use a rougher copper or a reverse treated foil. And reverse treated foil means the matte side now is the side that gets bonded to the prepreg. And the shiny side is treated and gets bonded to the core. That's what reverse treated foil means. So what that means is now you have a reverse treated foil for the power layer, which is actually the ground to your strip line. But that's rougher now. the reverse treated foil. And that's where you have to really watch if you have high speed and it's near where you have a power layer, which is the ground of the power pair. You usually have a power and ground sandwich in a core. And you usually put the ground as a reference to the signal layer. So that's one application where you could end up with the two different roughnesses. And another application is in HDI design, high density interconnect packaging, where you're actually building up now every layer with microvias now. So when you're building up, you're putting in the prepreg, and then your board shop is putting the foil on. It's much like in standard PCBs, where the outer layers, the board shop puts that foil over on the prepreg. And usually that foil is rougher and, for peel strength or whatever. So if you don't specify that foil, you could end up being rougher in a build-up, HDI designs as well. So all I'm getting at is when you do your stack up, you just have to be cognizant of this effect and understand, that roughness matters, and, where you put your high speed, looking at things on it. Yeah.
Yeah, this is interesting. And, we've been talking about like taking a value from whether it's a statistical value that you determine yourself, right, from distribution, or whether it's a number provided by the foil manufacturer, whoever gives it to you, right, and doing that for prediction. But there's another set of techniques that involve actually the one that I know of best is it's not really a regression technique, but it's a genetic algorithm technique that intends to extract a roughness correction factor as a function of frequency, and then taking that, turning around, and using that in prediction. And so the idea being that it's essentially model free, right? It's just extracted directly from measurements. And so there's this one paper from like 2009 where they apply this technique to S parameters to get all the parameters in the transmission line, and then you could add in roughness as one of those parameters. So you get a kind of a roughness profile versus frequency. What are your thoughts on that? Or are you an advocate of you need to just determine the roughness parameters directly from some measurements or from statistics?
Talking about, I do know that the modeling tools have certain roughness models included in them. So you really have to kind of put in parameters for that roughness model, for the tool.
But what I mean is like those models are analytical.
They apply it to the conductor part of the roughness or loss, because your loss has got dielectric loss and conductor loss. And of course, there's a skin effect we all know about, and that's that's just normal. But the actual roughness now, adds more loss to it. And the Hammerstead had a simple correction factor. It's just an equation that they apply, and they apply it to the actual conductor loss itself. S parameter. And it just adjusted it correct for it. The Huray model is the same thing, only it's a little more complicated. It needs the two parameters from it. So either way, you need a correction factor to apply to your to your thing. Your S parameters, you can't just apply a number sort of to that, because it's a combination of dielectric and that. So, before these ADS tools, EDA tools had the Huray model in, I had to break it down. In fact, my 2015 paper was virtually analytical, where I applied it, to the copper part of it, and then the dielectric loss, and combined them afterwards. but you have to apply it to the conductive part for it. So, yeah, I'm not familiar with what you were describing.
Well, what you end up getting out of that is basically like a table of values, which is copper loss versus frequency, and so it kind of lumps together a roughness factor and skin effect, skin resistance, right? And the skin resistance you can factor out because we know it's dependent on square root of frequency, so you can factor that out, and you're just left with a think of it as just a table of values, right? Column A is frequency, column B is roughness correction factor. So if you had that data, does that provide any more value, or is that really just an extra analytical step that forces you to go right back to taking roughness measurements?
If you get some number, how do I now apply it to anything? Is what I'm getting at.
Yeah, because in the Huray model, right, you can, like you said, you can calculate a roughness correction factor. But if you could instead extract that from measurements as a function of frequency, instead of calculating it at every frequency, and then turn around and use that data to then predict another type of transmission line,
those numbers
let's say.
Into a model, right? You're going to get a model. You're going to get these numbers out of something. It's a nice table. You've got this loss, but now how am I going to take those numbers and put it into a tool to do modeling? Like, I don't know how to do that. And why?
Yeah, you'd have to write something custom to do that. Yeah. I like that perspective because I ask this sometimes because you see these techniques sometimes in academic papers, and this particular one was an IEEE paper, but it was it's academic paper, and sometimes those things don't scale very well. They're very nice conceptually. The nice thing with academic
papers are, initially they may find, they show things, but if you read some academic papers, they may spark some other idea, and they do have value.
Sure.
I mean, let's take the Huray model for instance. When they came out, there was an academic paper, I think 2008ish or 9ish, first presented IEEE things, and it had a lot of mathematical theory, and it was physics based and a whole bit. And he developed this equation to apply to it. But again, nobody, you could now use this in a tool and tune what you said, but your tool would have to have some properties in it, so you tune these things to make it match. So it did end up being eventually practical because now they have included in actual EDA tools. For instance, Altium uses the Symbior engine underneath now. And Symbior engine has Huray model under it, right? So the nice thing about my Cannonball arrangement is, even though the Symbior doesn't say Cannonball per se, model, it still uses Huray. And my Cannonball part gets you the parameters to feed into Huray even. So some tools have Cannonball-Huray directly, where all you put in is RZ number, and it works under the hood and gives you the thing. Other tools ask for Huray, but the Cannonball method, it gives you the radius, what you need, and it gives you the area, what you need. And the number of spheres is always 14. And the nice thing about the Cannonball, simplification, I call it, is, some tools just ask for SR and R. So SR will always end up being a constant, because things cancel out with it. So all you're left with is a radius needed. And the Cannonball method is 0.06 times RZ gives you the radius that you need, and there is a constant. So Symbior, the constant for they ask for a constant. There's one number. Other tools, it's another number because it uses a different part of the equation. But I did my 2019 DesignCon paper. It's on my website. it goes in there. I've got a table in the slides showing these tools, like use Cannonball-Huray directly. Symbior would use this, and it gives you the constants to use. So it's actually quite simple. My Cannonball-Huray method is the simplicity of the old hammer stud method, where it just asks for the RMS number, but it gives the accuracy of Huray. So if you're used to using a hammer stud, the Huray, this method will find it get more accurate. So I encourage people, if they're interested, they can go to my website. I have publications on there, the DesignCon papers, and plus how it was all derived early on. You can follow the papers and find the history, but the latest one on there is more practical now for people to use. So it's quite good, actually. I'm quite happy with it.
That's excellent. And we will definitely link to your website in the show notes. So I encourage anyone who is out there listening or watching, please head on over to Bert's website, check out those papers, and learn as much as you can about this important topic. I think we're going to leave it there for now, but I want to thank you so much for coming on to the podcast. This is a treat for me because, as I said earlier, I have cited you many times, and I have other work that I'm doing, hopefully to submit to DesignCon for this year myself, where I am citing our guests.
Well,
so
thanks
this
for
is,
having me, Zach.
as I said, a real treat for me. Thank you.
Look forward. One day we'll catch up. If you're going to DesignCon next year, hopefully I'll be able to get out there. I missed 2 years now. So hopefully January we'll be able to get together. Wow, I don't.
Absolutely. I don't drink, but I'll buy you a
partake
beer.
very much anyways anymore, so doesn't matter.
That's all right. And then a Pepsi or something. Thank you very much again for being here, Bert. Everybody, this has been Bert Simonovich from LambSim Enterprises, signal integrity expert, and I encourage you to check out his website, check out his DesignCon papers, learn more about all of these important aspects of high-speed design. With that, make sure to subscribe to our channel, hit the like button, and you'll be able to see all of our upcoming podcast episodes as they come out. Last but not least, don't stop learning, stay on track, and we'll see you all next time.